Um, I don't know if you guys heard about Stephen Hawking very much. Stephen Hawking passed away a couple of years ago. And Stephen Hawking had an article before he died about the universe and God. He did not believe in God, all right? Which is fine. So what he did, he made a universe from scratch, from nothing. In fact, he figured out how you can make a universe, the entire universe, without a creator. But he needed one thing. That one thing is what I believe is God. All right, that's my belief, anyways. And I don't mind putting it on tape so everybody can see it. I'm not embarrassed. And that's the laws of the universe. These laws of the universe are so impressive, first of all, and we don't really understand them. We know that they work, we know how they work, but we don't really understand where they come from. I mean, really, seriously, have you guys ever thought about where do the laws of the universe come from, right? So to me, that's where God comes in. Because without the laws, there would be no universe. But if you do have the laws, you can make the entire universe from nothing. You don't even need space. You don't need time. You don't need space. You don't need anything at all. Nothing. Non-existence gives us existence as long as you have the laws. So these laws of the universe are really impressive. Now, there are forces in nature, and you might think, oh my God, there's so many different forces in nature. But in reality, there's only four forces in the entire nature. That's it, four forces. So we're going to be talking about those four forces in nature today. And as we talk about these forces, we're also going to elaborate on each force. And today we're going to be talking about these forces. And then I'll elaborate on one of those forces called the electromagnetic force. Electromagnetic force is light. And even though light looks, simple and it's just light, and you're all looking at light right now and all that, in reality, it's amazing. It's just amazing. What light is and how it works is just totally amazing. So let me get my new camera. You guys can judge to see how well this new camera works. And let's see how this new camera works. All right, so there's my new camera. And I can go to the board and I can do this. Aha. And so I go, okay, so at what point would you guys like enough magnification? I think that's pretty good, right? So now I have total control of what part of the board I can show you without actually going to the screen. Isn't that awesome? It was only 135 bucks. Pretty cool. All right. So let's write down these laws of the universe. I'll give you the laws first, not necessarily in order of the strength of these laws, but then I'll give you the laws in order of the strengths afterwards. Now, there's something called force carrying particles. So what is a particle, first of all? Particle, normally we say, like atom is a particle, right? It's like something small, we say, that is, let's say, moving, could be a particle. But you can also treat things like a spaceship as a particle. So let's say a spaceship is going to Mars, but the shape of the spaceship is really not important. The spaceship can be, with 2 wings, 3 wings, doesn't really matter. You can still treat it as though it's a particle, right? So you can even think of a particle as a planet or asteroid or something. Doesn't necessarily have to be an atom. But when we talk about force-carrying particles, we're talking about these really impressive things that are really, really, really tiny, incredibly tiny, and these tiny things carry forces. As an example, a photon is a particle. So this photon particle, we say, is light. But not really. Photon is the carrier of this thing we call light, all right? So these are the force-carrying particles. So for every force I'm going to give you, I also give you the force-carrying particles. So if you see me in the street behind a car, that's the vehicle that is carrying me. It's not me. My car is carrying me. In the same sense, a photon carries this force that we call light. In fact, its real name is electromagnetic force. All right? So let's see what these forces are. So I'm going to write down forces of nature. The forces of nature. The forces of nature. And the very first force that we're going to talk about is the one that most of you are really familiar with. It's called gravity. And gravity is the weakest force in nature. It's incredibly weak. How weak is it? Well, look, the Earth has got a lot of mass, incredible amounts of mass as compared to me, right? And it's pulling me down towards it. But look at me. I'm just going to beat up gravity. I just beat up gravity just by doing this. So I'm beating up gravity. So really, gravity is an extremely weak force. Why is it weak? We don't know. It's possible that gravity is the only force that leaves the universe. And it goes forever anyways. Like, let's say this pen here that I have, it's got mass. Because it has mass, it has gravity. So the gravity of this pen goes throughout the entire universe. It goes through the walls. It goes through whatever you can imagine. It goes all the way to the end of the universe. It never stops, right? It's called gravity. So let's start with this thing we call gravity. Gravity is a force number one, gravitational force. And we say it's always attractive. There could be another force called anti-gravity, and maybe that's the fifth force. In fact, when we talk about anti-gravity later on, how the universe is expanding, we think this is, we call it dark energy because we don't really understand it. But this could be anti-gravity, actually, that makes the universe just get bigger and bigger every day. All right, so gravity is carried by a particle. So this is carried by a particle called graviton. So this graviton is not gravity, it's the particle that carries that force we call gravity. All right, I want to make sure that's clear. Number two is light. And light has a name. We call it the electromagnetic force. So when you see stuff like light, what you're looking at is electricity and magnetism. Wow, what is that, right? So we say this is the electromagnetic force. Electricity, electromagnetic force. And this electromagnetic force is carried by a particle we call photons. So this electromagnetic force carried by a particle named photon, right? Photon. So it's a pretty impressive thing. Now, we're going to be talking about photons today. We're going to be talking about light today and how it travels, what it is, and it's incredible. And when I tell you about it, you might not even believe how fantastic and miraculous this thing is.
Could I ask a question?
Yes, of course.
So are these particles visible separately from the forces they carry?
Well, that's a very good question, actually, right? It's an extremely good question. These are particles that are, none of them are really visible per se,
Okay.
right? Its existence is inferred basically by the forces themselves.
Okay, thank you.
Does that answer your question? You're welcome.
Yeah.
Like, we've never actually seen a graviton, but we've noticed a gravitational wave that went by. You know, have you been reading about gravitational waves? We just detected them a couple of years ago. Actually, it was 4 years ago. There's waves of these gravitons, but an individual graviton has never been observed, basically. All right, so number three. I'm going to kill number one so I can have enough room to put down number three. And these are the ones, the forces that you may not even know they exist. So number three, we have strong.
Let's go.
Strong nuclear force. So strong nuclear force. Strong nuclear force is only visible, or you can detect it, on a very, very, very tiny spaces, like inside the nucleus of the atom. Outside the nucleus of the atom, you don't even know it exists. So it's just only inside of the nucleus of the atom that it takes effect. Outside the nucleus of the atom, nothing. We didn't even know it existed until the 20th century. So it's kind of a weird thing. Now you can see one proton, right? One proton is a nucleus of an atom. It's called a proton, right? Now we'll talk about what's inside of this because there's also 3 other things in here called quarks and all that. We'll talk about that later. But a proton has something called charge. You see I have a positive thing here called charge. That's the electromagnetic force. So atoms not only have the strong nuclear force, they also have electromagnetic force, charge. Now, if you have one, we say this is hydrogen. The number of protons determine the elements. We'll also talk about that later. So one proton, hydrogen. If you have 2 protons, oopsies. So you have 2 protons, and now you have helium. So number of protons determines the element. Like uranium has 92 protons. So if you have 92 protons, you have uranium. 1, you have hydrogen. 2, you have what we call helium. 3 will be like lithium. But now here's a question. Protons are positively charged, right? Positively charged. And positive charges will repel other positive charges. So in fact, between the protons, there is a repulsion. If in this room we have 2 protons, they will approach each other and they will repel each other like this. So they can't even get close to each other because they're both positively charged. They repel each other. However, if you get them close enough, then there is this force that comes out of them. It's called strong nuclear force. It's carried by this particle called gluon, like a glue that glues these protons together. Once they're glued together, you can't take them apart, right? It's incredibly solid. This is the strongest force in nature. We call it a strong nuclear force. It holds the nucleus of the atoms together. Incredible force. So we say this is the strong nuclear force carried by a particle. Called gluon. So gluon is not the strong nuclear force. It's a particle that's actually exchanged between these protons. They give each other some. One of them says, let me give you some gluon, buddy. No, let me give you some gluon. So they keep exchanging this gluon. That's why 2 protons stick together and become helium, like that. All right, so this 4th one, also kind of unknown to most people, it's called a weak nuclear force. And this weak nuclear force is the force of destruction. It makes things fall apart. It makes the universe fall apart. If you come back to this universe like in 500 billion years, there'll be nothing left. Not even atoms are left. All atoms are decaying. This decaying force is inside of the atoms themselves. So not only this construction is built into the atoms, also the repulsion, the force that makes them fall apart, decay, right? So, wow, destruction and construction, they're all there. And so we say this is the weak nuclear force. So we say weak nuclear force, weak nuclear force. In fact, all the atoms are going to go away. The last atom to go away is hydrogen atom, which is just 1 proton. And in about 500 billion years, even that's going to disappear. So the universe is going to be dark. It's going to be cold. Nothing there. Not a single star, not a single planet, nothing. It's just going to be one empty universe, dark, empty, dingy, terrible place, I guess. Weak nuclear force. 2 particles carry this. Carried by Z and W bosons. This is responsible for something that we call radioactivity. So like as an example, inside the Earth, there's this radioactivity going on all the time. So what does this radioactivity do? Radioactivity makes atoms fall apart, like uranium. It falls apart after, God knows, in 5 million years, like half of all, uranium is gone. It becomes lead. That's radioactivity. It emits all these particles as it decays. And so that's weak nuclear force. That's responsible for the decay of the atoms. So that's the fourth force.
Could I ask a question?
Of course.
So radioactivity, that is what X-rays are, right?
No.
Okay.
No, X-rays are actually light. You
Okay.
see
So
them.
X-rays don't break down our cells.
No, X-rays are light. No,
Okay.
yeah, they don't fall apart. No.
Thanks.
They last forever. Yeah, you're welcome. All right, so now if you want to put them in the order of the strongest to the weakest force, that'll be a little different. So the strongest force in nature is a strong nuclear force. So this is strongest to weakest. Strongest force to weakest force. Number one is strong nuclear force. Strong nuclear force.
Oh shit! I hate.
All right. Let me see. Somebody's microphone is on. I don't know. You guys, if you not want to talk, just leave your microphone off, please. Okay. So strong nuclear force, number one. Number two is electromagnetic force. Electromagnetic force. Extremely strong, this light that we're talking about. As an example, like I'm standing here on solid ground. I should go all the way to China. I'm just should go through the Earth, come on the other side. So what stops me from going through the Earth? Well, it's the atoms in my shoes and the atoms on the floor. I have electrons in my shoes. The floor has electrons. Electrons are negatively charged. The floor has atoms. They have electrons negatively charged. My electrons in my shoes and the electrons on the floor, they repel each other. And as compared to gravity, light, the electromagnetic force, is 1,000,000 billion times stronger. Incredible, right? So normally we go, gravity is so much stronger than light, but no. Light is so much stronger than gravity, it's not even comparable, right? So that's electromagnetic force, number two. Number three, weak nuclear force. And then number four, gravity. That's all there's left now. The weakest force in nature is gravity. Even though it holds the universe together, all the galaxies are held together, the solar system is held together. On a grand scale, it appears that it's the dominant force. But on a small scale, nothing, right? Now, here's the thing. If you look at the atoms in this pen, right, just this pen, not very big, right? It's kind of a small pen, maybe, I don't know, an ounce, something like that. If I take the atoms in this pen and I extract the energy that they have inside, this strong nuclear force that they have in them, the stuff that is holding these atoms together, I'll be able to destroy the entire Earth if I could extract the energy inside of this pen. So strong nuclear force is that strong, or incredibly strong. That's the one that gives us the nuclear bomb. That's the one that gives us the hydrogen bomb. Those things are strong nuclear force, right? We just don't see it every day to day-to-day life because they act on a very, very small scales inside of the nucleus of the atom. They're fantastic. Outside, we don't even detect them. So outside, we only detect the electromagnetic force and gravity. These two forces only inside of the atom. Now here's the thing. Where did all these forces come from, right? We'll talk about this later too when we talk about the creation of the universe and all that. But I'm just going to tell you, it's very, very possible. We know at least 3 of these forces are just one force in different forms. So we don't know for sure about some of these, but we do know that these 3 forces, well, I'm sure it's all 4 forces. There was just one force at the very beginning. So when the universe comes into existence, right? Big Bang, you've heard of a Big Bang. At the time of the Big Bang, at the very, very, very beginning of the Big Bang, there's only one force. And they call this the God force. As the temperature of the universe went down, one by one, these forces split up. So one force splits up. Like as an example, we know for a fact that extreme high temperatures, electromagnetic force and weak nuclear force become a single force called the electroweak force. Somebody won the Nobel Prize in 1980s for that. So we do know, but we can't generate enough energy to actually see the nuclear force, electromagnetic force, weak nuclear force, and gravity to become one force. At the beginning of the universe, temperatures were amazing, like trillions and trillions of degrees. So we can't regenerate that kind of an environment. Not even in the Switzerland, where we have this synchrotrons, atoms going around, protons hitting antiprotons and all that. We generate a lot of energy, but not as much as we need to create the temperatures of the Big Bang. So maybe someday. All right. Any questions about these 4 forces then? So we have 4 forces in nature, and that's it that we know about, right? Maybe there's a 5th force, we said, anti-gravity, but we know about these forces. So we're going to be concentrating on the electromagnetic force now. The electromagnetic force is light. And this light travels in waves. Okay, what's a wave? So a wave is this energy that repeats itself kind of a thing, right? So like this is Queen Elizabeth giving you a Queen Elizabeth wave, right? She does this. She gets on, I don't know, she gets on her carriage and goes, you poor people, I am the rich one. You guys don't know, but I am superior to you. That's that kind of a wave, right? And it keeps repeating itself. So these waves, you can have a rope. You shake the rope like that, continuously repeats itself. Okay, that's a wave. Ocean waves, they're waves. Now, when you look at the ocean waves, it's not that in the middle of the ocean there's a wave, and that wave comes, carries the water from the middle of the ocean all the way to the shore. The wave is moving through the water. So it's not that the water is moving, it's that the wave of energy is making the water go up and down, and this wave moves, we say propagates, right, all the way to the shore, like that. So let's take a look at one of those waves. So here's a wave at the ocean here. There's a big wave. Here's another big wave, and so on. And I'm going to lay down on the beach. I'm going to be laying down on the sand. This is my eyeball. And I'm laying down on the sand, checking it out. And I'm counting the number of waves coming in from the ocean. I go like 1 wave, 2 wave. In, let's say, 1 minute, I detect 10 waves. So we go, there is 10 waves, 10 ocean waves coming in per minute. So when we say 10 ocean waves coming in per minute, what we're referring to is something called frequency. Now, what does frequency sound like? Sounds kind of scary, right? Frequency sounds technical. How frequently, right? How often? That's all. How often? That's not difficult to understand. So how often is Queen Elizabeth doing this? Like 1 per second, maybe? That's per wave. The ocean waves, 10 waves per minute. So how would I describe a frequency? We'll say number of waves per unit time. That's all. So frequency is the number of waves per unit time. Okay, so number of waves per unit time. Time. Okay, now there's a unit for this. The unit is called hertz. You may have heard of hertz. If you haven't, we'll talk about it in just a second. So the unit for frequency, how often a wave is, observed, unit is hertz. That's the number of waves. And what's the unit of time that we have? Seconds. So number of waves per second. Now, your computer, when you buy a computer, you go, okay, how fast is my computer? You go, well, your processor is 4.3 gigahertz. What does that mean? Gigahertz. Well, giga, right? Giga means billions. That's giga. Giga, billion. Mega, million. Tera, trillion. So we don't have that fast yet. We can't say tera, but we can say gigahertz. That means that your chip in your computer is doing that many operations. That's the clock inside the computer that you have, that chip in the computer that you have. So that's the frequency of your computer. Maybe you can do 1 billion operations every second, something like that, right? All right, so giga, billions, mega, millions. And this we call frequency. How often, right? Frequency of the wave, number of waves per unit time. Now,
I'm sorry, so in terms of how it works in a computer, so there are waves of is it electromagnetic waves?
yes, it is electromagnetic waves.
In the computer.
In the chip of the computer, yeah, it's generating.
Chip of the computer.
That's right, yes, absolutely.
How
Okay,
can
now,
you measure something like that, 1 billion per second?
with frequency counter.
Okay.
Saying, I don't work on computers, but I'm
Okay.
just saying, Okay, now the distance between the peak of one wave in the ocean, the peak of another ocean wave is called, so here's a peak, right? Here's a peak of one wave. Here's a peak of another wave, right? Here's the peak. We say the distance between the peak of one wave and the peak of the next wave is called wavelength. Wavelength. So maybe the ocean waves have a wavelength of, I don't know, 30 feet. The distance between, I don't know, if you're a surfer, you would know like how often these waves come in. You would know the peak of one wave, how far is the next wave. I assume every day that changes. So yeah, it's the peak of one wave to the peak of the next wave, the wavelength. So how would I describe a wavelength? I would say wavelength is the distance between the peak of one wave to the next wave. So that's the wavelength. Wavelength. The distance between the peak of one wave to the next wave. The peak of one wave to the next wave. like that. Now, it also has a unit. The unit here must be really, really small because light waves have a very, very, very short distance between the peak of one wave to the peak of the next wave. So now we have to go like billions of a meter. What is a meter? A meter is about 40 inches, it's about this big, right? And originally it was a unit that was described as 1/40 millionth of the circumference of the world. So if you go around the world and come back, it'll be 40 million meters or 40,000 kilometers, whichever. So nowadays we use the wavelength of light to define what an actual meter is. It's about 40 inches anyways. You don't have to know exactly what it is. So now we have a unit that we use to measure this wavelength. Unit is, right, nano. Now you've heard of nanotechnology. Nanometer. So what's a nano? These are all French words, right? Nano is a billionth. It's a billionth of a meter. So that's 1 divided by of a meter. That's a really, really tiny distance. Now we're talking about the size of the nucleus of the atom. So we're using the size that is really, really tiny. One billionth of a meter. We're defining that as a unit to measure wavelength of light. Really, really tiny, right?
So this is just of light.
Yes. Well, you can use whatever you want if you have tiny waves. So when we say nanotechnology, they're talking about like a pill. Let me see if I can find a pill to show you. All right. So in the future, Linda, when I'm dead, they will have pills like about this big. You eat this pill, it goes through your body. It's got a computer built in. It's got a video camera. It's got everything built in. It goes in and it checks your body. It comes back and says, oh, you have, your sugar level is high, whatever, your stomach acids are low. And they're already doing that. So everything is built into this little tiny thing. That's what they call nanotechnology. So everything is shrank down, like miniaturized basically. So that's what the nano is famous for right now, but basically means a billionth. Nanometer means a billionth of a meter. All right. So now we're ready to talk light. Incredible stuff, you guys. So light. Let me kill this waves and everything. So wavelength is the distance between the peak to peak of a wave. Frequency is how many times per second this wave comes in, right? So if you have 10 waves a second, there'll be 10 hertz. Hz is how they write it. If you have 1,000 waves per second, there'll be 1,000 hertz, like that. That's what hertz is. Now, they also use it in music. So sound is also in waves, but sound waves are very different. Sound waves are really cool, actually. And the way they travel is like a wave that goes through the air. So as I'm speaking to you right now, your microphone is reproducing my sound. And the molecules in the air, right? There's a whole bunch of air stuff in between us. So I'm vibrating the molecules in the air from your microphone or your speaker to your ears. They're vibrating and they travel like an accordion, like this, like that. Molecule to molecule. They travel a lot slower than light, but they still travel like that. All right, and then you get you to your ear, your drum vibrates, and then I don't know, there's more to it. I'll show you maybe if you like. I can show you exactly how it works until it gets to your brain, and then you detect it. It's incredible stuff. Those are sound waves. They also use hertz. So if you're into music, you also use hertz. It's not just light. All right. Now, when we say light, we say light is carried by a thing called a photon. Photons travel straight. I know. You've seen photons travel like this. There's a reason why they do that. But photons travel straight. They don't travel in waves like that. A photon, as it travels, it has actually two waves in one. One is the electricity wave or electric wave. One is the magnetic wave. And the way they travel is like this. So here is electric wave. And like that, it rotates. Okay. And then you also have a magnetic wave. So a magnetic wave is something that you have noticed around magnets. If you have seen magnets, you've seen magnetic properties. There is a magnetic field. There's a field, force field, basically. You can't see it, but it's there. You can use a magnet to pick up stuff, and you've tested the magnetic wave. You know that if you get two magnets together, it's impossible to shove them together. There's a force there, right? So there's a force. You can't see it, but there's a force field. So as the photon travels, there's a force field. This force field gets stronger, gets weaker, stronger, weaker, stronger, weaker, stronger, weaker. And that's what we call a wave. So really what we call a wave is what we call the amplitude, or like the strength of this electricity and magnetism, or a strength of the magnetic field and electric field. Increases, decreases, increases, decreases, actually goes to zero. So let's say this red stuff is electrical force. So this is electrical force. This one is magnetic force. And they're also, as they travel, they're perpendicular to each other like this. And they travel, they rotate as well. So they rotate, and the two fields, they get stronger, weaker, stronger, weaker. I can't really show it to you here, but I have a little video that I made that I can show you. So let's take a look at the video to see how this thing actually works. Let's see if I can find it. Right. All right. Can you guys see this?
Yes, Professor.
The electric waves are represented by the yellow arrows, and the magnetic waves are represented by the blue waves. They're moving perpendicular to each other, and they're also rotating as they move from left to right. The amplitude is changing, which is the strength of the magnetic field or the electric field.
All right, let's do it one more time.
The electric waves are represented by the yellow arrows, and the magnetic waves are represented by the blue waves.
Okay, so these are the yellow ones. I said they're electric field or electric force. So here's electricity, basically. It's getting stronger, stronger, and strongest. That's the peak. So from this peak to this peak, that's the wavelength, right? From here to here is the wavelength of this wave. Now, you can see it's getting stronger, 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 strongest, weaker, 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 weaker. It goes to zero. Then it regenerates itself, kind of like a lizard losing his tail, and it keeps growing it. And this thing does it forever. It's incredible. It's like the energy is reproduced. It regenerates itself, and it goes on forever. It never gets tired, ever. It can travel for billions and billions and billions of light years, and still with the same energy. It doesn't lose energy. This is pure energy. And so this is a photon that travels. As it travels, it has an electric field, electricity, magnetic field, and this magnetic field and the electric field, they also rotate. So their direction is changing and their strength is changing. They go to zero and they regenerate.
They're moving perpendicular to each other, and they're also rotating as they move from left to right. Yeah.
Isn't it incredible that what you're looking at right now is electricity and magnetism? Did you guys ever imagine you'd be looking at electricity and magnetism? And you
I have
call
a
it
question,
light,
Professor.
right? We call it light. I think it's just incredible. It's the most amazing.
Professor, I have a question.
Yes, please.
So these waves travel in space, so they go across something. When the wave gets at its peak, does it have a width, or what does that peak represent?
It's a field, right? It's a electric. So normally you don't have just one photon, right? You have a bunch of photons. And so it depends. Like what you call polarized light as an example, right? Polarized light, it only does this. So instead of rotating, it just does this. Keeps traveling in one direction like that. That's polarized light. So you put a polarized filter on your camera, you detect only polarized light. So that's like the direction is only fixed. It doesn't go around anymore. It just goes one direction. That's polarized light. Now, if you have a whole bunch of photons, you just saw it, right? It just rotates. So you have a rotating electricity, basically, right? Like this. So when you say the width, it has to do with the amplitude or how strong they are, the strength of the field, right? That determines, like you say, how thick is it or what have you. Do you follow what I'm saying?
Thank you.
You're welcome.
I have some questions also.
Yes,
Do
please.
so this is specific. What you're showing us right now is specific to electromagnetic force.
Electromagnetic force. That's right.
Electromagnetic force.
Yes.
Do they always look the same size as their counterpart?
Same size as what? I'm sorry.
Well, because they seem to be mirroring the size of each other on your display, and
Yeah, the electric field and the magnetic field, they peak together and
okay,
they drop together. They peak together and they drop together. Yes.
okay.
Simultaneously. You're right. They're synchronized. Yeah. All right. Now we're going to be looking at all of the waves that we call light in nature. So we're talking about all the light waves now. We call this the spectrum of light, the variety of light that there is. Just because, as human beings, we categorize everything, everything is categorized. You name it, I'll tell you the category. So we say electromagnetic spectrum, the electromagnetic spectrum, light. And light is not just what we see. What we see is a tiny fraction of light. Besides that, there's all kinds of other light that we don't see. So we're going to start with the ones that are highest frequency. High frequency means this. This is high frequency. Every second it goes like that. Low frequency is low frequency. High frequency, low frequency, like that. Okay? So we're going to start with the highest frequency and the shortest wavelength. Now, how fast does light travel? Speed of light is about 186,000 miles per second or 300,000 kilometers per second. So if I shine my light towards the moon, it'll get there in 1.25 seconds, like that, right? And it keeps regenerating itself, never getting tired. My flashlight will go to the end of the universe. It just takes time because it doesn't travel infinitely fast, only 186,000 miles per second, right? So now these guys here are called gamma rays. And gamma rays are shortest wavelength. So the distance between the waves is very, very, very short. Look, this short, right? Tiny. But the highest frequency, because they all travel at the speed of light, when their frequency is very high, the wavelength is very, very short. The distance between the waves are very, very short. So we say shortest wavelengths, shortest wavelengths, highest frequency, highest frequency. So these babies are humming. They're the most energetic of all the waves. The only use that I've seen so far, like in human endeavors, is surgery. They have gamma ray knives. I had a student in the class, and we went to UCSD, actually. She needed a ride. And there they had surgery. She had epilepsy, which means behind your ear, there's a storm of electrons behind your ear here. And so that's why you pass out, too much electricity for your brain to handle. That's called epilepsy. And so then you pass out, there's just electrical signals, there's just too much in your brain. So they actually cut that out with gamma ray knives, basically. Now, next, remember, gamma rays have a variety of gamma rays. Some that have a little bit higher frequency, some that have a little bit lower frequency. The ones that have the highest frequency are called hard gamma rays. A little bit less, called soft gamma rays. So hard gamma rays will have highest frequency and shortest wavelengths, right? And so soft gamma rays, you have a little bit more, a little bit more, a little bit more, a little bit more, longer and longer waves, and the frequency is going down. So as we go to the right here, frequency is going down. That means the energy is going down too. The more you do this, this is a lot of energy. This is a lot less energy. Like if I got slapped in the face, go like that, that's a lot of energy. Oh, it hurts. But if I go like that, that's like nothing, right?
So are wavelengths and frequency always inverse to each other?
Correct. Only in the case of light, though, not ocean waves or other waves.
Okay.
And I'm going to ask you why at the end. I'm going to be done in a few minutes. I'm going to ask you why do you think that is. So now wavelengths, wavelength. That means the distance between the peak to peak of a wave, like this distance here. That one is going up. They're getting bigger and bigger. The distance between the peak to peak of a wave is getting bigger, right? So wavelengths are going up, frequencies going down. Next, we have X-rays. So X-rays, gamma rays, X-rays, they have a little bit longer wavelength. So the distance between the waves is getting a little bigger now. But the frequency is going down. They also have X-rays that are, soft, and they call them soft, and they have some hard X-rays. So hard X-rays will be the ones that have the highest frequency X-rays. Soft X-rays will be the ones that have less frequency. They have less energy too. So the ones that have highest frequency, they'll be the most dangerous for us. If you're exposed to gamma rays even for 1 minute, you die. All right, so in fact, one of the things that happens when there's a nuclear attack is gamma rays. They'll kill you. It's the gamma rays that really kill you. All right, then we get to ultraviolet, UV, ultraviolet. So now we have stuff that we still don't see. A little bit longer waves. Still don't see them. These are invisible to the human eye. Waves are getting longer and longer between the peak to peak of a wave. Frequency is going down, not as often now. So less and less energy as we go on this way. Less and less energy. The most energetic will be gamma rays. And as we go down here, we have visible rays. These are the ones that we can see with a human eye now. So let me see if I can show you guys something here. Like if I have a white light, if I have white light, can you guys see this? So here's the colors. Can you guys see the colors now? This is white light.
Yes.
So the blue would have a higher frequency. They're the more energetic ones. The reds will be the least energetic, like that. All right, so let's start. I don't have all the different colors of pins, but I do have blue. So on one end, the highest frequency, the ones that are most energetic will be violet, blue, and indigo, right? Violet, indigo, and blue will be the shortest waves. The distance between the peak to the wave for visible light, they're the shortest distance, but they have highest frequency. Then we have green. So if you have green, then you have longer waves here. So the distance from the peak to peak is a little longer now. And then red will have the longest wavelengths amongst the visible. Right, like that. So you can see the waves are getting longer and longer, and the frequency is going down. These are visible. Beyond the visible, we have, again, stuff that we don't see. That we call infrared, beyond red, infrared, infrared, beyond red, longer than visible rays like that. So now the distance is getting longer and longer. Now this is heat, right? So heat travels at the speed of light. Heat is light. So when you feel the heat is traveling at the speed of light, you never want to look into a building that is on fire because it will burn your eyes, right? It travels at the speed of light. So then we have microwaves. Mostly for communication. We also call microwaves radar. So radar, microwave, same thing. The cops have a gun. It's called a microwave gun or radar gun. They shoot the radar gun at you. When it bounces back from your car, they can figure out how fast you're traveling. Which is pretty cool, I guess. So microwaves have a longer waves. Right, longer wavelengths. Frequency continuously is going down. You can see it from left to right. Frequency is going down. Wavelengths are getting bigger. So one of them goes up, the other one goes down. Wavelength is going up. Frequency is going down. Now, I guess I better tell you something about this microwaves. One of the things that generates microwaves is this, your cell phones. And I definitely will ask you guys to remember, don't sleep with your microwave, basically. This is your microwave generator. You don't want to sleep like this all night. You also don't want to probably put it in the back pocket. You know, who knows? We don't really know. Nobody's really doing any research. So, you know, in 30 years, I could get cancer. But then there will be no Verizon to sue, right? So Verizon will be gone. There's some other company that's going to come in. So I don't know. They don't even let people do research. In Europe, there's a few research being done. Here, not much. But I don't want to scare you because there's some videos on YouTube. They show you popcorn made by using a whole bunch of cell phones. I don't know if you guys have ever seen it. Like they put 5 or 6 cell phones. Somebody calls all the cell phones. They go on, and the popcorn starts popping. Those are all fake. It's not like that. But still, I know that these towers that they have, it's sending out microwaves. So how does that affect our brains? I don't know. I don't think anybody knows, especially 5G. So that's still a mystery, you guys. For that reason, I would stay away from them. Try to not sleep with them or put it on your person, on your body. All right, next we have radio waves, the longest of all the waves in nature, extremely long waves. You could have a wave as big as a mountain. So it peaks on this side of the mountain, the next peak will be on the other side of the mountain. Theoretically, you can have a wave that goes between here and the moon. It peaks here, then it peaks at the moon. So you could have a wavelength of 200,000 miles. Those are radio waves. There's no limit to the wavelengths. But the frequency, very low. in fact, what they call FM and AM. AM is called shortwave, right? But in fact, FM is a shorter wave than AM. So which one is a shorter wave, AM or FM? FM is a shorter wave, even though they call AM shortwave. And FM goes right through the atmosphere. It travels, goes, to other planets. And so that's what, can be detected from the Earth. So somebody will detect it in 10 years and go, okay, this is the dragons from Daenerys or something, in 10 years. You go, oh man, these people on Earth, they still have dragons, right? Because this FM goes all the way through the atmosphere. That's what they would detect like in 10 years from some other planet. Now, question. Let's see who can answer this and get a point. If this was a horse race, we want to know which one of these horses will hit the bottom of the blackboard first. What would that be? Which one of these waves will hit the bottom of the blackboard first?
Radio waves.
Thank you. Radio waves, very good. Anybody else wants to chime in?
Wouldn't it be the same time?
That's right. Very good. Is that Mr. Farmer?
Yeah.
Aha, I knew it, Mr. Farmer. Thank you. You remembered. They all travel at the speed of light. These are all light. Radio waves are light. Microwaves are light. Infrared heat is light. It travels at the speed of light. They all travel at the speed of light. Very good, Mr. Farmer. Thank you. Oh. So this is the nature of light, basically. And in astronomy, we depend on this. You can't just go to Saturn every day and check it out. What we do, we analyze the light. So you analyze the light from far away. It takes millions of years from other galaxies' light to get here. But when it gets here, you can analyze it and see what it's made of. You can see how fast they're moving away. There's a lot of information that is hidden in light. And so that information is what astronomy is about analyzing the light, basically. And you don't have to go to Mars to figure out what the atmosphere of Mars is made of. All right.
Could I ask another question, please?
No, you can't ask any more questions, Linda. You're done.
I know. Now, are these, have these all been seen or are they theorized?
No, these are all been seen. We detect them. We
Okay.
can't, when you say seen, that implies human eyes. You have detectors. So you have gamma ray telescopes detects gamma rays. X-rays, you've seen X-ray film and X-ray digital cameras now. Ultraviolet cameras, visible cameras. You also have infrared cameras, like infrared goggles. Microwave, same thing. You have antennas, right? You have radio antennas. That's how you detect them. But they're all light. They all travel at the speed of light.
I also have a question.
Yes, please.
So we've categorized these waves based on their wavelength and frequency.
Correct.
Would it be possible to have some sort of detector that could detect multiple of these categories, or is there a reason that we've categorized them this way?
I have no idea. I don't quite understand your question, though. What is it? What else do you want to know besides frequency and wavelength, though?
For example, we have cameras that detect visible light, but would we potentially be able to have cameras that detect ultraviolet and visible light at the same time?
Well, actually, the detectors that detect visible light, they also detect infrared and ultraviolet. But soft ultraviolet, not the ones that are super low. So you need a special detector for really, high frequency ultraviolet and X-rays and ultraviolet. Otherwise, the regular detectors in your cameras, they can see ultraviolet, they can also see infrared. All you have to do is to use a lighter or something, have a heat. Let me see if I can find a lighter to show you, because I think you can see light. Huh. Can't find a lighter right now when I need. Oh, here it is. See, let's see. Oh, it's this camera. Look at that. Isn't that bright? That's just a little flame. To me, it's not white. To me, it's super yellow. But here is so detectable, right, with your camera. So your camera actually can see infrared. You need a filter to filter out this stuff. So in your camera, there's an ultraviolet filter and an infrared filter to cut it off. They call it cutoff filters. So yeah, so detectors can detect all those that you mentioned. Does that answer your question?
It does. Thank you.
There's nothing special about what we see. In other words, we should have been able to see maybe infrared and ultraviolet, but because of our evolution and the light of the sun that is present on Earth, our vision is centered around yellow and green. We can see green and yellow the best. We can also see red, blue, but not that great. Our detectors don't really see red and blue as well as yellow. And then, you know, we don't see any ultraviolet or infrared with our eyes. Well, we can feel it. The skin feels ultraviolet and infrared. It's all evolution, you know, it's all evolution. If we lived on some other planet, we didn't come out of the water like we did come out of water, we would have been different species altogether. I think cows can see ultraviolet. Snakes, they can see infrared, right?